All right, welcome everyone. We're super excited to have the three of you here today. For the audience, this panel is on lessons learned scaling ML systems. And we have three experts in the room who have seen a lot of this firsthand. I'm really excited to have them and start talking about what they've gone through and what they've learned building incredible robotics programs at different companies. So maybe we could start out with folks introducing themselves. Danielle, if you'd like to start, and then Hussein and Bart sharing a little bit about your background and what you're working on.
Yeah, absolutely. Thanks. So I'm Danielle. I'm the technical director of machine learning at iRobot, the makers of products like Roomba and Brava. We're doing deep learning solutions, reinforcement learning solutions for millions of robots in homes worldwide. And excited to be here.
Hi, everyone. My name is Hussein, and I work at Cruise. We're an autonomous vehicle company. I'm the VP of AI and machine learning there. So my team builds the perception and prediction systems that run on the car. It also builds the machine learning infrastructure that we use to build these models, including the data science and machine learning deployment teams. So super excited to be here.
Hi, that leaves you with me. I'm Bart. I'm VP Corporate Development and Strategic Partnerships at Aurora Innovation, a startup company, with now 1,600 people that really focuses on building the Aurora driver. Really doing this not on my own, clearly, but with my great buddies from grad school at Carnegie Mellon. And what I do there is really look at opportunities to accelerate development, and I'm happy to be here. Thank you.
And my name is Russell. I'll be your host. I'm the head of Nucleus here at Scale. Nucleus is one of Scale's newest product offerings, a dataset management platform for machine learning teams. Before that, I started a computer vision company called Helia and was a senior machine learning scientist at Tesla on the autopilot team, responsible for the vision neural network. Super excited to have you all here today. And I wanted to just get right into what are the key differences between your ML life cycles and workflows from when you were operating at 1/10 of your current scale and now? What's changed? And maybe Hussein, you could start sharing some detail.
Yeah, sure. I think there are three main differences. The first and biggest one is reproducibility. Maybe 2-3 years ago, when we're much smaller scale, models were not reproducible or shipped without reproducibility in mind. The second big difference is the scale of training. So we now train on far more data than we have before. And then the third biggest difference is automation. So we are increasing the amount of automation we use to train more and more models without having our engineers involved. Those are the three biggest differences, I would say, compared to 2-3 years ago.
Yeah, great points, Hussein. I double click on all of those points because those are really good ones. Some additional ones at iRobot that we found really helpful in increasing scale is increasing testing at every layer. Because as you scale up and you find issues, as you always find issues, especially as you start to automate systems, you need to then know where did things go wrong. So increasing testing at the system level and then at the individual pieces lets you debug and jump into those parts easier. And then just absolutely agree on the data piece. At iRobot, we've created a data collection and data annotation team focused around machine learning algorithms. So having that dedicated team thinking about data has really helped us increase our scale a lot.
Yeah, I think we're all heading somewhere to a similar topic here, right? You're not building really ladders to get to the moon, right? We always said that, if you want to get to the moon, you need to build rockets, right? Collecting the right amount of data is key for this. When you begin doing this, every single data item counts, right? When you're now at this scale, it's not really that thing anymore. It's really what are the unique items, right? And it's really those important cases, right, in the long tails that we're going to talk a little bit later about, right, that really counts, right? So that's really a big difference between in the beginning when everything counts towards what is really important, right? And I also want to point out that not all cases are equal. You already mentioned this, that it is very important to understand how you validate. It really doesn't matter for me that the statistical performance went up on the average if what I now lost is, detecting one pedestrian, but I'm very good at 10,000 traffic cones, right? And so really being very explicit about what counts and what matters, what is that system influence of your performance. Yeah, I think that's a big difference from in the beginning when every single thing was awesome because it made it better. Now you have to be very precise about that.
That makes a lot of sense. Yeah, that move from aggregate metrics to kind of very specific measurements on all the different parts of the distribution you care about. So I guess to dive into that a bit more, a frequently encountered challenge that we've all seen of scaling ML systems is dealing with this long tail distribution of the real world. And it seems that at each increased order of magnitude of scale, you can encounter new, ever rarer edge cases. So what I'm wondering for you all is, first of all, how do you deal with that today? And what's the future here? What's the plan for the next order of magnitude and the next order of magnitude? Are we going to keep just constantly uncovering new parts of the long tail and always be debugging them, or is there a more scalable approach here? Yeah, what do you think, Danielle?
Yeah, so at iRobot, we take two big approaches. One is designing our data collection and model analysis procedures to purposely find those edge cases so that we can go after them and know what those are. The second big thing is thinking about how do we design the system as a whole so that the ML model can work in conjunction with other parts of the system, so that we all know that ML systems, data-driven, they're going to have failure modes. How do we make sure those failure modes still provide a good experience at the end? So thinking about those two is always trying to improve, but also knowing that these data-driven systems, they are going to have some weaknesses, and how do we complement those weaknesses?
Yeah, I think I agree quite a bit with Danielle here. You have to have a robust, fast, continuous learning cycle. So when you find something that you haven't seen before, you add it quickly to your data, and you learn from it, and you put it back into the model. But that's still reactive, and therefore designing your system. And I'd like to expand a little bit more about that, particularly focusing on high recall methods. So if you look at the autonomous vehicle problem, you can generalize the road into things that move and things that don't move. Like they have volume and they have velocity. And so you can still build high recall methods that operate at that highly generalized level, but then the rest of the system needs to react in accordance to that. And this brings up uncertainty. So you might not, you have high recall, but you may not be super certain what exactly this object is. And therefore the rest of the stack may need to drive the car a bit cautiously for a second or two. And us as human beings, we do that. So I think that's a solvable, or you can sort of make the long tail tractable that way. The third point that I'd like to add is that there are a lot of product tricks. And so there was a video where the Cruise car with our CTO, Kyle, and Sam, the CEO of OpenAI, and essentially our Cruise car witnessed a sort of funky construction vehicle at an intersection, and it seemed as if the Cruise car just handled it naturally. But what really happened in the background is, as we approached that intersection, before we got there, the car notified remote assistance, and someone took a look and just quickly charted the path around it, and with minimal disruption to the user experience. So there are product tricks that you can deploy, to Danielle's point, that help you sort of, again, make the long tail tractable.
I don't think you should call that tricks, because I think that's really the solution, right? As we pointed out already here, right? And all you say the same thing, right? It's very careful system architecture, right? We have to build safe systems, right? And that's just one single component. It needs to be a strategy, right? From day one, we knew that these edge cases were going to make or break a product, right? So focus on like being good at dealing with edge cases is extremely important, right? And you can't do that by relying on just one single component or network, right? When you look at, for example, unprotected left turns is always one of those examples where in self-driving, people look at performance, right? It's really going to be like, how many of those cases have you seen, right? And how do you perform in those, right? And making sure that you're really getting towards the end of that, right? I think also very important, and you also mentioned that, what is this sort of generic case, right? We have this philosophy that no single measurement can be left unexplained, right? If you don't know what it is, that doesn't mean you should stop reasoning about it, right? Because there's something there, and maybe your model hasn't figured this out yet, but it is important, right? So really sort of that system approach, I think, is key, and I think we all agree to that.
Yeah, I think we do. Maybe I've labeled it as a trick. It doesn't make it any less important, to be honest, Bart. But the thing is that I see is people often obsess about solving the long tail for one model. You have one model, devoid of any ecosystem, devoid of anything around it. And solving that problem is extremely huge. Luckily, there are domain tricks, system thoughts, whatever you want to call it. There are domain aspects that you can benefit and leverage that help you make the long tail tractable. So I think that is doable. And I often see a lot of people in the AI industry tell me, how are you going to ship a car? Like, how are you going to handle the long tail? This is impossible. No one has solved that. You need artificial general intelligence for that. But that's when I explained that there's a lot of more, that there's a lot of things that you can leverage to actually solve that.
Yeah, I think that's a super interesting point, and it's one trend that just we've been seeing more generally at scale, and especially internally, where for our machine learning systems, we are very explicitly kind of trading off between, okay, how much of the distribution can we capture with machine learning, and then where can we augment that solution with human intuition to kind of completely solve the problem. And depending on the domain, right, in self-driving, there are latency requirements. There's a lot of tricks there, and whether you call them tricks or system architecture designs to make sure that you can safely transition if you're going to make that transition. But I think one general thing we're seeing is, as long as you can architect that system in such a way that you can make the trade-off and go from model to person, you just get better over time, right? The people fill in the gaps, and then your system gets more intelligent. You have fewer gaps, and I think that segues into this next question, which I wanted to get at. And maybe Bart, you could tell us from your perspective, both as a PhD roboticist and a leader at Aurora on the technical level and at the kind of strategic partnership level. How does this approach, as we're describing right now, scale to the next order of magnitude? And is that something that, obviously there's going to be more system architecture, system design, but are there new things you plan to kind of introduce, new processes to help keep making this better?
Yeah, that's a very interesting question, right? Because we talked about like, how do we go from where we were to where we are now, right? And it's where do you put your next best efforts, right, to make that count for you, right? We've always been setting very outrageous goals for ourselves, right? We acquired a simulation company to really get a boost in getting started on making that simulation as accurately as we can to represent the world, right? And so allowing that, right, allows us to really sort of put that focus on that. So like, that is just a continuation of what we're going to do, right? It's a very large problem that we're going to solve, and we can't just do this ourselves, right? And so we continue making these investments on better infrastructure, right? Better technology, new technology. We don't have everything ourselves, right? And so I see improvement on ML platforms as being one of those key measures to do this, right? But also keep making internal investments as well, right? We spend a lot of time collecting data on various platforms, so the Aurora driver could actually be independent of what architecture or vehicle class we are going to put the driver on. And so it only took us 12 weeks to bring up a truck after we've only been driving beforehand on minivans, right? But that's really because we're looking at the problems that we're going to solve ahead from us, right? And try to make investments currently today that will actually grow with us, right? So really looking in the future helps you do that. And that's certainly a question also from what are the technologies what we need in the future. And I think one of those things specifically that are useful, better tools for identifying how do you get reliable networks, how do you make sure that when you learn something new, right, that you can incorporate that quickly in your stack. Those are all important aspects to that. Just continue making those type of investments is what I think is going to happen.
Bart, you summarized it so well, hard to add on. I guess the only other point I'd make is just continuing more automation. So every aspect of the puzzle pieces that you need to put together to build the solution. So for example, Bart mentioned simulation, synthetic data, like all the data annotation. Where are pieces that you're doing to get to that scale, and how can you automate more and more of those pieces so that you can scale up exponentially?
Yeah, totally agree. I just want to maybe dive in a little bit in terms of simulation. I think simulation is extremely important so that we can, as our head of simulation say, abuse the car virtually in all sorts of ways. And this is not just for testing. It actually helps you accelerate figuring out the long tail, accelerate understanding the limits of your system. And you could leverage actually machine learning to train models that try to get your system to crash. And that is extremely valuable. And when I say crash here, I don't mean crash as a system failure or unhandled exception. I'm talking about like where your car would be unsafe. And so I see that as an extremely valuable tool. The point that Danielle mentioned about synthetic data, I actually see significant amount of value there. I was personally sort of very skeptical about this, but recently at Cruise, we've seen data that demonstrates you could even leverage synthetic data for training perception systems. And I think that is going to accelerate how we deliver safe systems and how we can span into multiple cities. So these are very exciting things. The other thing that I just want to mention also a little bit more concretely is there needs to be more investments in understanding the performance of robotics within the environment they're at. This is non-trivial. So when you compare machine learning in a company like Google or Facebook, these operate in the data center, so they're fully instrumented. You can easily generate data about where your models are doing well and where they're not doing well. Now, take that to robotics, where you have a vehicle or a Roomba or whatever it is, it becomes several orders of magnitude more difficult. And there's a lot of innovation there. And I do believe that if we can accelerate that process of capturing data from the environment, diagnosing it so that we can understand which parts of the system are responsible for these errors, this will be a massive step function in our capabilities to deliver such robots in production. So it is going to take some time, but it is definitely one of the biggest investments. And I think companies like Scale can actually deliver a lot of value there too.
Yeah, can I add something to that, right? Just to give you a sheer magnitude difference, how that is important, right? So when we are going to make the first unprotected left turn, right? Again, that example, right? We actually had like 20,000 hours of really practice of really doing unprotected left turns in simulation before we had done a single physical one, right? That's 227 million or so, right? Left turns in simulation, right? Now, if you look at what somebody does for a driving license, maybe like what, 50 hours of supervision before they get let loose on the road, right? So I think you're really pointing out what is important, right? Being able to do this safely, virtually, right? But making sure that it's realistic, right? And so that what you actually prove out in simulation actually holds for the real world. And as you pointed out, that's going to be key to be successful here. Yeah.
Yeah, I wanted to dive in, Hussein, what you were talking about. It's super interesting on this kind of synthetic data component as well, and simulation more broadly. So when we're talking about this, just to be concrete, there's many different sensors on a robot, right? And so what are we simulating here? And do you think that the kind of learnings from your experience, do they translate to other machine learning tasks if we're not doing robotics?
I don't know really about non-robotic applications with regards to simulation. I think simulation is far more relevant in perception applications. And so just as you said, and as you referred to, whenever there are sensors and you understand their physical capabilities, you can actually leverage simulation and sort of expose these sensors to circumstances that you may not be able to, or would be far more expensive to actually collect such data. Now, I just want to clarify that synthetic data will never be a full replacement to real data, but it actually enriches the data set. It may mean that you don't have to collect as much, or you actually can collect data you may never be able to collect for various reasons. So I think, as I mentioned, it's complementary. And I think it's going to be extremely useful for robotic scenarios because the interesting thing about simulation is this concept of fuzzing. What you can do is, if you understand your environment and you have a couple of pivots, you can then vary these pivots far more than what you could see on the real world. As an example, if we want to collect data related to emergency vehicles, there's not a lot of them actually in San Francisco. In fact, even motorbikes, there's not a lot of them. But if, these are particular motorbikes, these are users that you would see in emergency vehicles, you would also see, even though rarely. And so simulation can play a massive role there to enrich your data and put your emergency vehicle in various different circumstances that you may not be ever able to collect because it's such a rare case.
Makes a lot of sense. Thanks for clarifying. And I wanted then to go back to an earlier thread that's maybe somewhat related to this, which is the question of how do we then measure the performance of these systems? If we're doing well, we're doing well in this scenario, in this scenario, in this scenario, maybe even more broadly than just the system level metrics. Like, what are the most important metrics? They could be anything, some way of measuring your team's productivity, some way of measuring your model performance, some way of measuring your system. What are the most important metrics that the three of you care about when you're kind of scaling up these ML systems?
So I'll give a couple of funny ones to kick us off, and then I'll let Hussein and Bart put in some more real ones. But I always talk with my team on a couple of KPIs. One is how many solutions are in production providing real customer value. I think in ML and data science in general, inside robotics and other domains, there are so many cool techniques we can use. There's so many cool approaches we can use. There's so many potential solutions, but just focusing around what are solutions that make an impact to the customer and are running live in production. So just keeping a focus on that. And then the second one is one I call like a tell a friend KPI, which is terms of not obviously like measuring model performance, measuring system performance. Those things are very important, but how many iterations do you go where you make such a jump step in your solution that you would tell a friend about it? Like, we weren't using synthetic data before, but now we're using synthetic data and we are way better than before. And you're so excited about it that you'd want to tell a friend. So we call that like the tell a friend type of KPI. So those are two ones that we think about.
I actually really like the tell a friend KPI, because we have a dashboard in the company where we actually basically use that as the tell a friend, because we're doing this with our friends, right? And so why is this important? Because it's again that systems approach, right? Like, if you just made your traffic light detector better, right? How does that really impact the overall system, right? You as an individual working on that with your data set, right? That's very difficult to judge if you're actually helping, right? And so setting up your KPIs so they all sort of string together into overall system performance, so that you know that if you improve this, it's going to help the overall system. I think that is very key. So these compound KPIs, right, that are still individually meaningful, that is, I think, one of the techniques to do this. You also mentioned another one that I think is really important, right? How quickly can you actually get something from new and you never seen it before, or this is one of those long tail events? How quickly can your system now become better, right? That's just measured in time. It's a very concrete one. I think we all can easily agree on that. That's a really important measure. And why is this important? Because there's always going to be new things to learn, right? This is the whole game of level 4 autonomy, the operational domain, right? If I want to increase my operational domain, right, and it's safely, quickly, broadly. So yes, broadly, right. That means we have to address new data, new items, right, new scenarios, right, and how to bring this in and then quickly make a better system, right, is also one of those key metrics. So I think you pointed out, even though I think you have much lovelier ways to call them, I think the key ones that sort of measure what is sort of like the thing that you actually can count and get the system to be better, but also that you can actually do the whole operation of making the system better quickly.
I think all of the metrics mentioned are very useful. I do believe there's one or two very powerful additional metrics. When you build these simulated environments, or even your offline replay testing environment, you want to measure how it correlates to sort of the actual environment in the world, because if it doesn't correlate, then the metrics you're going to be uncovering from it are not may not direct you in the right, may not give you the right direction, essentially. And so at Cruise, we've spent a significant amount of time and effort making sure that our offline tests and our simulation environment is as correlated as possible to the real environment. And it is not an easy job because the real environment changes, traffic patterns, the proportion of driving during the day versus the night, the proportion of driving in different neighborhoods, they all have different characteristics. There might be some unplanned events which adds additional pedestrians. And as we know, this makes the driving situation more complex. So it's very important that any robotics company understands sort of, or tries to understand the statistical composition of the environment where the robots operate, and then bring that to their offline world and make sure their offline world is balanced towards those statistical compositions.
So what do you do? Okay, you're measuring overall system performance and you're measuring your traffic light detector performance, and you've improved your traffic light detector, but there's some hidden coupling in the tracker system, and the Kalman filters are now, because the model is better, the overall system is worse. So how do you have kind of every engineer who's working on an individual experiment testing everything, or how do you make forward progress?
So if you look at sort of what our virtual test suite is like, right? It's all about scenarios that are important and happen in the real world, right? What is the performance of the overall system on that, right? Now, you can still track your individual KPIs and how well do you do on your traffic lights, right? But while you do those experiments, right, it also gets rolled up in these virtual experiments, right, that are like simulating a whole drive, right? Sometimes with real data, right, because we can just replay that to some extent, and sometimes it's completely newly created environments. So I said the tools that we built out early on were really to get a very accurate simulation of our sensor suite. It's actually very important, right? Because we're making our own sensors, right? It's not that I'm going to first hand over all my trade secrets for my FMCW LiDAR to somebody who's going to make me a simulator, right? But so we do want to simulate that also quite accurately, right? And so it is indeed very important that that correlation is very strong, right? Because otherwise the results that you get in your virtual test suite, right, don't really mean very much, right? But yeah, the volume needs to be, done in simulation, because we can't drive enough miles ever to convince anybody that, the system is safe if you have to do this with a real vehicle.
Yeah, and I think the scenarios where an individual model metric might improve, but the overall system might decrease, those are awesome scenarios to figure out why does that happen, and is your validation set in that individual scenario actually representative, or is the system level test not representative? Like, what is going wrong that is causing that? Because in general, if you improve part of the system should improve. Obviously there are exceptions, but those are really good cases to dive into. Why is that happening? Is there something in the data collection procedure, something in the simulation procedure? And focusing on that will help the overall system improve.
Yeah, great point, Danielle. Generally, this problem of changing a component in the system that may impact upstream or downstream components, it's a very complex problem, and it's one of actually the most complex challenges that robotics engineers face. The more you invest in simulation, the easier it becomes, because they can discover these problems ahead of time. And sometimes they can, obviously they need to solve them before they deliver. That said, I think the most important aspect is you solve problems from an end-to-end perspective. I often see when people are more focused on solving the performance of a model, they're probably not thinking about the problem end-to-end. And often what happens is that they may actually improve. I mean, the worst scenario is they improve the performance of the model, but nothing happens downstream, because if, let's say, the car starts detecting car doors that are being opened, but the planning system does not react to that, then you've built a feature that no one else is using. So the way we do it at Cruise is we encourage folks to work more from an end-to-end perspective. And that way, they're already thinking about the impact of these changes downstream and upstream, and they deliver sort of an end-to-end experience versus, just improving a model in a silo without understanding how the rest of the system needs to react or leverage the outcome of this model.
We have one question from the audience to just add a little more color there, which is around, so when you are using then this simulated data, how do you make sure you're not overusing it? You're not overfitting to the simulated environment. How do you manage that domain gap?
I think that's with all data, right? You cannot train on your test set, right? And so like you have to be just very careful how you use data, right? So there's no difference there for with synthetic data, right, versus real data. Like, you know, you need to be honest with yourself there.
I think at the end of the day, we have to have live tests so that we detect whether we are overfitting or not. And so that is sort of a safety net there. But then, as we discussed, the correlation aspect is the antidote to reduce sort of your overfitting on a simulated virtual environment that doesn't represent anything. So it's a great question, but that's why we've also invested in correlation. And it's not just for simulation; it's even for your tests where you actually replay actual data. So if you're testing, if your test population is more during the day than you actually drive in the night, then you have a gap there. So so again, as I said, correlation and making sure you have enough coverage is critical here.
Makes a lot of sense. And I think one theme from a lot of these answers is there's a lot of infrastructure here. There's a lot of testing infrastructure. There's a lot of workflows so that when you do run these experiments, you can validate them. And so I want to talk a little bit more about that. And you know, there's been, I think, in the industry, a broader conversation of this concept of software 2.0 and machine learning being in many ways a fundamentally different mode of development than traditional software development, where we're maybe lacking some of the tools that we really have well established at this point for traditional software development, like CI/CD, version control, code review. Like, what does code review look like for 100 million neural network weights? So I'm curious if any of you have kind of taken some inspiration from those existing tools for traditional software development, and what have you learned trying to maybe translate them to a machine learning first mode of operation?
Yeah, absolutely. At iRobot, we think a lot about how can we, Hussein actually mentioned this towards the beginning, the reproducibility aspect. How do we think about the entire system being able to reproduce, to understand where and why things happened? Obviously, sometimes it's very hard to get perfect reproducibility, but thinking about what are the aspects that matter, thinking about version control of models, thinking about like a model registry, thinking about data reproducibility and where did that come from. We have an interesting aspect of iRobot where we need to respect the right for data to be deleted from our testers. And so how do we deal with model reproducibility and the whole thing around when data is deleted from within models? We also invest a lot in CI/CD around things like Python packages, Docker images. So how do we make those workflows easier and share knowledge and share tooling around the team? So that all of those things are a really big investment for sure.
Yeah, and so if you look at how we look at that at Aurora, right? If you look at the software team, they have a tenet that's called carry our water. What that really means that we're all responsible not only for the work product of maybe the model that you just trained, but also like getting the right tools together, right? There's no point for everybody to write their own little Python script to do something, right? Yes, if you look at software engineering as a whole, right, there is a fantastic suite of tools that you can just buy off the shelf, right? That's kind of my job, to find some of those unique tools that can help with that, right? I wish there were those unique tools that actually can help me end-to-end on all my machine learning models, right? Now, there have been actually some startups in this space that give you some interesting pieces over there, but there's no actual complete tool chain that I can just put to work, right? And so yeah, that is something that we just somewhat have to build ourselves, right? And we're doing this because it's not quite out there, right? And that's a team effort, right? But those tools really need to make sure that they can deliver on what is actually expected from us, right? We're building here a safety critical system, right? And it's only as safe as we can make it, right? Based on the tools that we have, right? So if we can indeed not guarantee integrity of data, right? How do we ever update a model when that is needed, right? And so, yeah, we need a lot of tools around that to help us. And now there's just a lot of, tool building going on, right? again, back to these, have to build, rockets to get to the moon and not ladders, right, to get there, because it's just a much harder problem and the tools aren't as mature. So we do a lot of that ourselves, but it's a very big investment. And unfortunately, I think everybody's doing similar things there.
I want to maybe shift the question a little bit. Like, what is the difference between building ML and robotics versus machine learning that has been done in many big companies for more than a decade, right? I mean, I believe that potentially Google was one of the first companies that developed a very large scale machine learning model, maybe by 2004, 2005. So we're talking about 15 years of machine learning development. I think what is unique about robotics, and it turns out is a big gap in traditional ML, traditional ML applications like commerce or search or ads and so on, is that you really need to understand your input distribution. You really need to understand where are you deploying the system. You cannot just make trade-offs there. So as an example, in the ads world, as long as you're 1% or 2% or 3% better, you can deliver the model. But that might mean that you've traded off one cohort above the other. And that's why some social networks have problems where their ad system are biasing against colored users. Now, in robotics, we can't do that, or especially in AV, we can't go and say, well, our system works really well with silver cars, but it doesn't really work so well with yellow cars. But since there's far more silver cars, it's okay, we're 1% safer, let's ship the model. We can't do that. We have to understand the input distribution. And that's the reason why I think machine learning for robotics may not suffer the same problems with bias and unfairness that other machine learning systems have suffered. And this is a completely new concept in development in general that you don't even see in normal software development.
Yeah, I would chime in that the observation of making these kind of aggregate trade-offs for edge case trade-offs, it is definitely a recurring theme. And I don't think you can escape it, whether you're an ML system for robotics, an ML system, a computer vision system for retail, or any number of these different domains. There's constantly going to be, as machine learning pervades more and more of these societal systems, it becomes really important to not just work well enough, but also have the auditability, have the measurability to know that we're serving all the different groups, and in this case, vulnerable road users, that we're doing a good job on all of them. And I think that makes a lot of sense. So I would love to, given that it sounds like you've all implemented many of these systems yourselves to kind of do this analysis, have there been any surprising or unusual or really tricky bugs that you've discovered where it was maybe at the intersection of multiple systems, or something that the process of solving that really illustrated why some of these investments paid off? Danielle, I don't know if you had anything to share.
Yeah. So at iRobot, we're constantly developing new products. So those new products have new sensors, which obviously means the data for those new sensors will be different. So at the beginning of the life cycle of new products, we need to collect data to make models for those new products. And one thing that we do, when the hardware and the software is not yet ready, it's not as easy to collect the same distribution of data as you're going to get when that product is ready. So one simple example you might be able to imagine is we might use a camera sensor to collect images of kitchen tables, so that we can build experiences that do things like, Alexa, clean under my kitchen table. But if we collect still images of all of the kitchen tables, but then in the real world, the Roomba is going to be driving around and getting motion blur. So that distribution of the data that we collect is often really tricky to figure out. Is the collection data going to be similar enough to the production data that we're going to be able to have that same level of performance? So as we scaled up our systems and built in more automation, built in more testing, it allowed us to figure out where those types of errors were and to figure out what to prioritize on the data collection front in order to improve the systems.
Hey, Danielle, so you have a whole data kind of collection and curation team you mentioned. And I guess that I would be really curious to understand, both for you and for other folks as well, how do you prioritize what unlabeled data to label, right? Because one thing we've seen both ourselves and among our customer base and the kind of machine learning community more broadly is that there's this kind of there's this evolution that machine learning teams go through where, all right, we've collected our data, let's randomly sample some subset, send for labeling, oh, we've got a model. And then as people start realizing, oh no, we need it to work better and better and better, people get more sophisticated about that curation component. So yeah, would love to hear how you prioritize what unlabeled data to label at this point.
Yeah, absolutely. So a few different factors. The first is diversity. So diversity of places around the world, like Roomba, for instance, has to operate in all the places in the world. So diversity of environments, diversity of locations. Then the second main one is model in the loop sampling. So figuring out where is the model not working well, like the highest loss, issues with the model, and sampling based on that. And then the other one is simply spatial sampling, because we care, for instance, being able to understand what the different furniture items are, different things within the home. So leveraging other sensors or other metadata that tells us about the uniqueness of the data point. So diversity, uniqueness, and model in the loop.
Yeah, I think those are like two questions in there, right? Let me maybe start with the first one, right? Our mission at Aurora is really to deliver the benefits safely, quickly, and broadly, right? Safety is really critical to everything we do, right? And so when you say insidious bug, right, that's something that I have to have caught in my virtual tests already, right? That's where I need to catch that. Not only then, if I catch it then, that's an opportunity to learn for the long tail, right? Because, hey, I hadn't seen it before, but it's important, right? So it goes directly in our list of, new scenarios, right? New events, right? And this is also how you get curated data, right? That's sort of your second question, right? So how do you manage a stream of data? How do you understand what is important? Yeah, we have a triage team for that, right? We're really going to look very carefully at these events that, behavior is different than expected, right? And then we're gonna understand like what parts of the system work, what didn't work, right? And then collect examples of that, right, in those long tails. So it's really a very meticulous process to look at, what is these events that you don't know how you perform yet, right? And collect a new bank of interesting scenarios in addition to all the scenarios that you already had, right? So it's again this whole scaling out of an operational domain, so that eventually we'll at some point have a level 5 system growing out of these, increasing larger operational domains.
Yeah, these are all great points mentioned by Danielle and Bart. I just want to add an additional category. Like, it's really useful to collect data on any use case where the system is making mistakes. Maybe not the entire system, but maybe a subcomponent of it, right? Now the question becomes, as our cars are driving or the Roombas are going around, how do you determine that? So we've realized that, a combination of rules, like to leverage auto labeling, or even machine learning models that try to estimate, well, it looks like something is funky here, right? The car hasn't necessarily gone into a unsafe situation, but maybe there's a pedestrian far away that we should have seen and we're not seeing, or maybe there's a vehicle that we're not estimating its dimensions correctly. And so we actually found that potentially if you could use some machine learning models to capture these samples, and some of these learning techniques to enrich the samples you capture, could be very, very useful here. And I think there's going to be some more innovation, because what you really want to do is you want to turn every mile where you have a car on the streets, whether it has a driver behind it or not, you want to turn every mile into an opportunity to learn something. But in order to do that, you need to automate the ability to say this piece of data is useful versus not. And just doing random sampling will very unlikely help you.
Totally. I think that's such a good point on in some ways, the kind of model debugging process is very deeply tied to the data prioritization process. And this is on my mind a lot, as the three of you know, just from leading Nucleus, where the kind of primary goal is to help it make it easier to help people debug their models by debugging their data, and then improve their models by being really automatically thoughtful about what to prioritize next. One question we got from the audience on this topic is, how then do you measure, like loss, say, on unlabeled data? If you don't have the labels, how do you know that it's problematic?
That's a very good point. It's very hard to measure recall, right? It's really, really hard. And I don't think there's a good way to do that. That said, we have some proxies where we've already detected problems on the road, and we have that category, and it has some data points, and we use our automated techniques to see how many of these examples are relabeling as actually issues. So again, it's not a true metric for recall, but at least it gives us an indication that here's how much it's capturing out of what we know.
Yeah, and I would just say leveraging as much as possible other sensors or other information that give insight, or even other models. At iRobot, we have a very small chip on our robot, and we have to deal with the whole quantization of models aspect. And so a lot of times we can run much bigger, much fancier models in the cloud, and we can use those models to also help find issues with the smaller model. So just whatever other information you can use to help inform that model, those predictions, is often really helpful.
Yeah, we see that also very much the case, what you said, like all these other modalities, right? So we have quite a few modalities, right? And, using that also when we cross-label things is a lot easier, right? If I already have, some LiDAR points over there, and I have, camera image there, like now all of a sudden it becomes much more tractable to do something with that radar data, right? And so in that does help. But yeah, it's not necessarily an easy problem, as I'll point out. Right?
I'll chime in. The other things I've seen both in my kind of personal experience as a machine learning engineer, and then also helping other folks now with Nucleus, is that even if you don't have labels for your unlabeled data, you can still have model predictions, right? And so people can run one set of model predictions. You can potentially run multiple sets of model predictions. And there's a lot of active learning research around taking the kind of differences between that ensemble of model predictions and using that as a proxy for maybe loss or how tricky it is, as well as, for that subset of data you do have labeled, well, you can measure errors on that, and then you can find similar examples to the erroneous ones. And whether that's through the structured metadata you're talking about, whether it's through more kind of semantic similarity, there's a lot of diversity in how that gets done. But those are some other things that we see. I guess we're kind of getting close to time here, so I just wanted to ask you all, maybe upon reflection so far in your kind of careers as machine learning leaders, what is one ML process change or infrastructure investment that you wish you had made earlier? Now kind of seeing things from where you are. And Hussein, would love to start with you.
This is a really hard question to say, because I wish I've made all of them earlier. We have a very long roadmap and a lot of things to do. I don't think ML for robotics is there yet. It's in its infancy. So it's just really hard to choose. There's just so many things that I wish we had done already.
Totally, yeah. There's so much infrastructure investment and so many things that need to be built. One thing that I would call out is I wish we had focused a little bit on creating a machine learning data collection and data team that we talked about earlier. I wish we had done that earlier. We obviously have a lot of systems tests. We have a lot of testing of Roombas. There's a lot of data that's being collected through other means. But having a dedicated machine learning data team who can work with the machine learning engineers and can focus on what is the meaningful data collection that will impact the models. Doing that earlier in their cycle definitely would have accelerated us as well.
I think we're pretty aligned here altogether. So we have actually built out fantastic visualization tools now. And oh boy, we wish we would have done that earlier, because now we much better understand what we're actually spending our efforts on, what our KPIs are, and all of that. And so we really didn't know that beforehand, and now we do. And so we wish we would have known earlier.
Visualization, data curation teams makes a lot of sense. Sounds like some hard-won lessons from scaling ML systems in the real world. Thank you, Hussein, Danielle, and Bart, for spending time with us today. Really enjoyed the conversation, and thanks to the audience for tuning in. Take care, everyone.
Thank you so much.